In the late 1980s, the dream of the personal flying car looked exactly like this. The Moshier Aurora promised a future where you could step out your front door, hop into a sleek single-seater, and lift off straight from your lawn. Looking at this provisional performance spec sheet, the ambition is wild. It claims a top cruise speed of 530 miles per hour, along with a vertical takeoff distance of 0 feet, all wrapped in a footprint small enough to park in a standard home garage. But building a personal vertical takeoff and landing craft, or a VTOL, requires solving a massive mechanical problem. To generate enough lift to hover, you generally need an enormous exposed spinning blade. Traditional helicopters rely on these incredibly complex, heavy metal mechanical linkages, and for a suburban driveway, they are uniquely terrible. They're deafening, the open blades are an immediate hazard to anything nearby, and they throw out a chaotic, scorching wash of exhaust. Moshier Technologies proposed a radical alternative. They wanted to strip away the exposed mechanical rotors entirely and replace them with a completely enclosed system. To pull this off, they had to abandon traditional aerodynamic models and rethink how an aircraft handles airflow, relying instead on what they called fluidic propulsion. You can see this departure clearly in this front view schematic of the Aurora. The exterior geometry is completely smooth. There are no propellers, no overhead rotors, and no bulky engine pods breaking up that sleek UFO-like shape. Shifting to this side profile, the fuselage is incredibly compact. It features a sweeping aerodynamic canopy, and notice the absolute lack of a traditional tail rotor. And looking down from above on this blueprint, we see exactly how it managed those strict garage-friendly dimensions by keeping the wing structure tight and manageable. Because the exterior is effectively a hollow shell, the aircraft's mechanical workload is shifted entirely to its core, where a high-output engine is mounted deep within the fuselage. Rather than attaching that engine to a drive shaft to spin an external wing, Moshier engineers designed the power plant to function as an enormous high-pressure air pump. This top-down internal wireframe reveals the architecture. As the central engine fires, the high-pressure exhaust is immediately captured and routed away from the core through branching internal channels. Follow those ducts to the edges, finding them terminating at 4 rectangular slots. This design leans on a physics principle known as the Venturi effect. When you force a high-velocity gas through a narrow pinch point, it creates a low-pressure vacuum that aggressively pulls in any surrounding, slower-moving air. Looking at this port-side schematic, you can see the Venturi effect in action. Large arrows indicate ambient atmospheric air sucked straight down through the craft. It hitchhikes with the fast-moving engine exhaust, massively multiplying the total volume of downward thrust. This mixing process solved 2 major problems at once. It generated the necessary lifting force without spinning an external blade, and blending in all that cool ambient air instantly dropped the exhaust temperature to levels perfectly safe for a neighborhood street. This front-facing diagram also shows how the pilot steered. By pneumatically opening or closing internal louvers over those 4 slots, they could control pitch, roll, and yaw simply by shifting the air pressure from one side to another. On paper, fluidic propulsion offered a mathematically elegant way to strip away the bulky, dangerous mechanics of vertical flight. Which leaves us with the obvious question. If this Venturi system was so safe, quiet, and capable, why did the Aurora never make it off the drawing board? The answer lies in the harsh reality of fluid dynamics. Air behaves exactly like a fluid, and when you force it to travel rapidly through confined spaces, it generates intense internal friction. While those Venturi slots successfully multiply thrust at the exit, getting the exhaust there is the problem. Forcing the engine's output to navigate tight corners and complex internal plumbing destroys a massive percentage of the raw energy before it ever reaches the outside atmosphere. Let's check that spec sheet one more time. The craft is rated at a maximum weight of 2,125 pounds. Lifting over a ton straight up demands an immense, unbroken column of downward force. Compare the Aurora to a standard helicopter. Those 4 restricted rectangular slots simply cannot move the same raw volume of air as the massive, uninhibited swept area of a traditional spinning rotor disc. Ultimately, the internal friction of the ductwork ate up too much power. The energy required to overcome those losses and lift the craft vertically was catastrophic, permanently grounding the Aurora as a beautiful paper concept. The Moshier Aurora remains a radical attempt to bypass the mechanical limitations of traditional flight through fluid manipulation. It serves as a reminder that while engineering can find creative detours around mechanical complexity, those designs must still reconcile with the fundamental laws of motion.